The next talk will be, I decided I'll just call it the JetBrains gang, because it's 5 people. I can't even read all the names because I don't have them in front of me. They will talk, as I said, about the biological knowledge base and about Web-MPS. So right now, people are showing up. Ekaterina is there, Elena, Simon. This is a load test for a StreamYard, by the way. We've never had so many people here. Hi, Daniil. Well, go ahead. Somebody probably wants to share their screen.
Yeah, I'll start. Thank you. So, hello, everyone. I'm really happy to present our project, Biological Knowledge Base, to the conference today. So, I'd like to start from the introduction of our team and overall agenda of the presentation. My name is Ekaterina Zemtseva. I'm a project manager at Genestack. I'll tell you about the entire project and its objectives. The demo of the product will be given by Elena Zimina, a front-end developer at Genestack. She is the best who knows the application from the user's point of view. Daniil, Elovkov, and Simon Alperovich are software developers at JetBrains. Previously, they worked in the MPS team, and Daniil developed declarative definition language for the MPS and created a code generator for Projectional Editor Web-based. Simon was in charge on Projectional Editor support and development. And now, they both are working on our project, and today, Daniil will talk about how B2B language is defined in program code, and Simon will present how projectional editing works from a server side. So I suppose the JetBrains needs no introduction in the audience. Let me speak a few words about Genestack. Genestack was founded in 2012 in Cambridge, UK, with a mission to address the biggest challenges in bioinformatics. At the moment, it's also located in St. Petersburg, Russia, and the new office is planned in Boston, United States this year. Our team consists of software developers in bioinformatics and biologists. Our expertise lies in storing and querying biological data, so-called omics data, which processed by pharmaceutical, consumer goods, biotechnology, and agri-science companies such as our customers, Roche, AstraZeneca, Corteva, and Unilever. For better understanding what we are doing, I would like to explain what omics data means. So it is a term that represents biological data from genomics, its variations in individuals' DNA, transcriptomics, how gene expression varies between samples or individual cells in different conditions, and proteomics, which proteins are present in sample and how much, and many other examples. I hope it's more clear now. Because of technological development, the amount of all kinds of biological data, such as this, has been sharply increasing. And here, we've come to the part explaining why the project was initiated. So no doubt that rising amount of biological information gives us more knowledge. But on the other hand, it makes working with information challenging. For example, in the area of drug discovery, one possible question is, does a particular substance, gene expression, or protein signature correlate with a particular disease outcome? Another example from the area of education, how a particular process correlates with another process, even if the processes are from different biological areas, and others. So, and which solutions exist? So it is the search in scientific articles and search in existing databases. Both options have their pros and cons. But considering examples I gave, I would say that the first option inefficient because of the large amount of data that biologists discover constantly. And for the second option, I would say that existing databases contain a limited set of data and don't provide any structure that would link them to macro processes. So, to help biologists with the issues mentioned, the main goal for the project was to create a repository of biological information in a structured form with the ability to query it. Here we connected a Genestack expertise in biology and JetBrains expertise in DSL. So the product we are creating is called a biological knowledge base. Knowledge base consists of a graph of processes and relationships between them. Each process is described by a number of parameters, such as biological entities, gene, protein, issue, etc., and changes to the entities, up-down regulation, drug treatment, dose, and duration. These parameters also describes the biological context. It can be record for each process, or the common context may be set for some of processes. And relationship between processes may be the following types: causal, correlation, logical implication. So the meaning is, I think that it's clear for the titles. So it is very important to note that structure allows us to connect processes from different biological areas. I mean that microprocesses, it is things happening in cellular level, may connect with the macro processes, its phenotypic changes, and also connect with biological areas. Its information is presented across all biological data. So, and I would like to show you a simple example. Here, I specified a context, said that organism is mouse, and describe a processes. So, the exposure to malnutrition in the intrauterine period, it is simple to say before birth, is leading to growth restriction and changing one of the gene expression of the pancreas, which is also leading to abnormal development of pancreatic endocrine cells, and which is leading to diabetes in adulthood. So this simple example showed us that we can link different processes from different areas. And also we can find connection between malnutrition in intrauterine period and diabetes in adulthood. So let's talk about how it can be used in practice. In terms of how to fill the knowledge base, the following ways exists. The first one is literature. Here in the picture, it's PubMed. So an unstructured information from the literature is encoded and stored in knowledge base using a combination of text mining and collaborative editing by scientists. In the area of text mining, there is another very interesting project at JetBrains. It's called Paper Analyzer. It is in progress, and we are planning to integrate with them in the future. So the second option is existing databases, such as Pathway, drug clinical trials, and others. And also a manual entering documents written in structured language. So from the business point of view, knowledge base is planning to use as open platform with crowdsourcing model like Wikipedia. And in this case, the users will be charged only for computation costs. And the other option, to use the knowledge base as a private knowledge basis for commercial customers. So now I'd like to hand over to Elena to give a real demo of the knowledge base. And please switch sharing to Elena's desktop.
Hello, everyone. My name is Elena Zimina. I'm a software developer at Genestack, and today it's my pleasure to make a demo of our application, which we are developing together with JetBrains. Okay, so our app looks like this. So here we see, here we see 3 tabs for searching the documents, for creating and editing them, and tab queries to make queries to our knowledge base. And let's start from the editing. Make scale a bit bigger. Okay, the main entity in our application is the document. And here on the left side, we see the document explorer. Document corresponds to the root node in MPS. So here, the documents are grouped by their concept. So we see here biological processes, relations, functions, and documents themselves. And here we can do the basic operations with the documents. So we can create a new document of a particular concept. Let's do it. So in the central part, we see an instance of the Projectional Editor. And here we can edit the document. To write something. We can delete it or publish it. What does publish mean? Well, we support the versioning of the documents, and publishing means creating of the revision of the document. So let me show you the example. Here it is. So the revision history looks like this. We started just with adding a category. A category means a tag. And then we added more variables and facts. And now our document looks like this. And we can create a new draft from any revision. And we can continue from any place of the document history. I must know that we are working with a real server running the application on Amazon, and I hope that we will not experience any network problems. But excuse me in advance if they will be. Okay, so let's go back to editing. And now I would like to show you our fascinating collaborative editing. So we created a document, and the other user can open it too. The working copy state exists for every user in our application. It is not like Git, where everyone has their own working copy, but rather like Google Docs. And collaborative editing works like that the users can see each other's changes simultaneously. Let's add the fact and write something. So you see that how it works. And this kind of magic is supported by our operational transformation server. But let's go back to the language itself. Of course, we are not the first who came with the idea of describing scientific facts and findings in computable language. In particular, there is a language called BEL, which stands for Biology Expression Language. Now it is a community-driven project. And we think that our language is better. That's why it's called BTB, better than BEL. And so let's write something in our language. I must say that this editor has zero common code with MPS. It is a completely separate project with its own code base. But we try to carry over the best practices from MPS. So we have similar mechanisms. And let's see how it actually works, how to write something in BTB language. You see that the document consists of fact sets. A fact set is a set of facts, and every fact represents some biological statement. So let's find some statement. I go to NCBI, National Center for Biotechnology Information, and I took a paper, and I would like to write in BTB a statement from the abstract. So we see there are two proteins, interleukin 10 and interleukin 12, and they are produced by pathogen-activated cells, macrophages, and dendritic cells. I've prepared a picture for you. Oh no, picture is here. Yeah, dendritic cell looks like this, and macrophage like this. And when they are activated, they secrete proteins. They are the cells of the immune system of mammals. So they work like this. And let's write it. Let's go back. So the first fact, we need to declare a variable macrophage. And a variable will represent an instance of macrophage. So let's do it. Macrophage. And we need to define its type. Where do the types come from? They come from ontologies. Ontology is another important concept in our language because it is critical that biological entities which we describe and use have consistent names with some common vocabulary accepted by scientific community. So we need reliable dictionaries. And there are some really good comprehensive public sources for definition of organisms, cells, proteins, genes, chemical compounds. I would like to show you the example. Here we see cell ontology. Yeah, and our macrophage is here, and its relations with the upper classes of the cells. Yes, so it's important for us that ontologies contain not only the list of the entities, but also relationships between them. And these relationships represent a large amount of already available knowledge. And we can use this knowledge for computer analysis of the biology data. Okay, it is important that we have imported some ontologies to our project. I can show you here. We have cell ontology, GBI ontology, NCBI taxonomy, and the others. Yeah, so we can operate with these vocabularies, and let's define the type of our macrophage. You can see that we have a bunch of autocompletes. Yeah, macrophage. So the first fact is that macrophage is activated. Cell macrophage. Where did this statement is activated come from? So let's go here. Yeah, here we see the process declaration. Another instance of our language, and we see that this process takes a cell as a parameter. So we can use macrophage as a parameter of this statement. And I go back. Okay, and the second fact is that activated macrophage secretes protein. Cell macrophage and protein. I go to the another ontology, uniprot, and I look for protein. Interleukin 10, yes. But we need to define that this fact is caused by the first fact, activation. So I add the causation arrow. Yes, and that's it. We described what we wanted. Activated cell secretes protein. But I would like to add, I would like to tell you about one nice feature. So now these facts look like function calls, and it is not very convenient for human beings, which will write the facts to our knowledge base. And we have a nice feature, custom editors. So let's go to the declaration of activated process. And here I'll show you this feature. We enable the custom editor. You see that the editor looks like the editor declaration in MPS. It consists of cells. The difference is that it is defined not by language designers, but by the users. So the real users, researchers and scientists, can define how the editor will look like. And I declare the second process, this one, secretion by cell. I go here and declare that's true. Editor, cell, secrets protein. Which protein? Our protein. That's it. So let's reload our editor and see. Yeah, so we see that now our statements look like they are written in natural human language. And if we add some more fact here, fact of secretion, secretion. Yeah, so we see that the editor itself has changed. Now it looks like like written in human language. Okay, so yeah, we can publish the document now. Publish. And I would like to show you one more real world example. This one. So we have imported the Reactome database. This is a comprehensive database of the pathways, so biochemical reactions in the organisms. So here we see the example from the Reactome, and this is a metabolic reaction which takes 3 inputs, ATP, cobalamin, and water, and produces 3 outputs, cobalamin, ADP, and this substance, I'll tell you how it is called, hydrogen phosphate. So yeah, we see the same in our language. We took 3 inputs, ATP, water, and cobalamin, and they have produced 3 outputs. So the real world reactions look like this in our knowledge base. Okay, and I think I can go to the queries. Computer analysis is a cherry on the top of the whole stuff. So as we have databases, ontologies, and the knowledge from the papers in one place, in our knowledge base, we can try to find some interesting connections between different processes and facts. And let's imagine that there is a researcher who may wonder, is there a connection between cell activation and protein secretion? So let's write it. Activation, and secretion. Secretion by cell. Excuse me, scale doesn't work very cool, but yeah. And we can run the query. And we see the result. Here we see the result chain. So we have found that activation of macrophage produced protein secretion. And we can make more complex queries. We can define the concrete parameter of the activated cell. So we can write macrophage here. So I won't do it now, but still. So yes, it works like this. And I think, I think that's all about the demo. Thank you all for attention. If you have any questions, please write them. And now, Daniil, could you please continue with the depth of the language itself?
Yes, sure. Daniil here. So, Elena has shown us what this B2B language looks like from the user perspective, and I will briefly show how it is defined by the programmer. So we've been working on this framework for defining languages for running projectional editors in the web. Framework somewhat similar to MPS in purpose, and it's been mentioned by codename Web-MPS. And since the last time we showed it, we have actually tried to migrate it to Kotlin. So let's see how it looks now. Well, knowing Kotlin syntax would be a plus, but that's not that important really. So from a very high level, it looks like this. So structure-wise, concepts such as Kotlin classes or interfaces. The rest of language definition is done via some Kotlin DSLs, rather lightweight at the current moment. Plus just some plain vanilla Kotlin code with a little bonus that the framework allows us to track what parts of the model were read during executing that Kotlin code, so that we know what it depends on. No code generation is employed currently. And another interesting thing is that asynchronous execution is kind of everywhere. It's supported natively by Kotlin coroutines, and it's a mechanism in the Kotlin language that allows to write the code in a sequential manner, in a very usual and conventionally looking way, but and have it run asynchronously, as if there were callbacks passed around, stuff like that. And that's very helpful in the situations when we embed our language or the editor into a client-server application, or when, for instance, resolving a reference requires contacting the server. Because contacting a server is always asynchronous, at least for JavaScript code running in the web. Okay, now in more detail about different aspects of language definition. So yeah, from this moment I will be jumping between the slides and the code. So structure, well, all in all, conceptually it's pretty much the same as an MPS, of course. So we have concepts, and they have properties, child roles, references. Just a couple of notes that can be interesting. So speaking of references, in MPS, we have what MPS calls static and dynamic references. In our framework, they're both kind of equally first-class citizens. They're both like two special cases of a more general thing. Next, so yes, concepts are classes and nodes are objects of those classes, obviously. But despite the fact that it's so simple, we try to separate where we define the concept structure or shape, that is, what properties or references it contains, and the particular implementation for nodes. So we can potentially have multiple backing data structures suitable for different scenarios for the same concepts, but in reality we only have one currently. So let's have a look at some code. I have idea here. Okay, and speaking of structure, so we have this B2B document concept, kind of a starting concept of our language. And just a Kotlin interface. Here we define multiple child roles. So it's a val inside the interface. It's like a field or a getter function, if you like. So here we define the type. It's a special kind of list because it's a multiple child role, and the concepts of children, child nodes. So over here we have something like a behavior method. I will talk about them later. All right, another concept for the notion of fact. We have here we define a single row child with a special kind of property. Well, the word property may be slightly misleading, but it's a single row child, and the type, the concept for the child node. Here, another concept for fact precondition, which Elena showed. Here we see how references are defined. It's just the word reference and the concept of the target nodes. So if we look at the implementing class, fact precondition import. So this is actually the place where we choose a particular implementation that will be used for nodes. So it pretty much mirrors the shape of the concept that I've just shown you, but adds some lower level and implementation details. So here, for example, we say that the same facts that we saw in the concept definition, we initialize it with a particular collection of children. We specify the concept. We specify some internal ID. For the reference over here, we Again, we initialize it with some implementation, pass again some internal ID of the underlying property that is used to store the reference contents. Here we have a reference to the actual data structure that is used to actually store data of our nodes. And well, that's pretty much it for structure. What I want to say that we plan to evaluate using code generation at least for structure, because currently we have to write some boilerplate code by hand as that import class that you saw. We also have some node factories, so it would be much nicer to have them generated. Okay, editor. Again, conceptually, it's pretty much the same as an MPS. So for a given concept, we define what cells the editor will contain. We switch on and off some parts of the editor. We define side transforms, delete transforms, we define completion, and we do it in a way that we start from basic building blocks, like this particular text results in this completion action, or like give me all possible target nodes for this reference, and I want to see them in the completion list. And then we combine them, those building blocks, transform them, and we try to do it in a Kotlin idiomatic way. We also support custom editors, as Elena said and showed. Those are not defined in your Kotlin definition of the language, but defined by the user in their model. And we only support textual notation for now. We plan to support other kinds of notations in a way conceptually the same as what I'm about to show you right now, but we haven't started that yet. So let's have a look at how editors are defined. So B2B document again. Okay, so we say editor of this concept, and then we just enumerate what it will look like. So it's keyword space, very simple things. Here we want to see the collection of children of this role, and if I navigate this reference, this is actually a reference to the role definition side, the concept definition. So we have some import statements inside a document, B2B document, and here we define the editor for them. The editor itself is very simple, not very interesting. Here we define a simple completion. It says that the user can type the word import and produce the node of the right concept. Here, for instance, we define editors for the whole hierarchy of concepts underneath this abstract value concept. And the completion in this case is slightly more involved. We have extracted it into a function. Here it is, so let's look inside, and it follows this pattern. But first we define individual completion lists, like this. In the end, we add them all up with the plus operation. And most of those individual completion lists have the form like give me all possible target nodes for this reference, and then with the help of map operation, we transform that completion into completion that will produce the nodes of the right concept. Here, for example, we use, instead of reference completion as the basic building block, we use integer number completion. And then we do a simple thing. We construct a node of some measurable value, and we set the amount property inside of it to be equal to the number from the completion. Okay. Now, variable reference value, for example. Okay, the editor itself is not very interesting again. It's trivial. It's just reference contents, or to be more precise, show me the reference target, because we can either show the contents of the reference itself or the target node. And what I want to show is here we define a right transform on it. We say right transform, and we define it in terms of completion again. We say that the user can type a dot, and it would complete. It would result in some model transform action described here. So another thing I wanted to show is when we want to either show or hide some part of the editor. So here we have the editor for ontology link. I don't want to go into detail what it means in B2B, but we want to either show or hide some part of it based on some condition in one of the answers to nodes. And we have extracted this logic into a separate function here, optional specialized link. If we look at it, first we define how this optional part will look. Again, it's very simple. It's some keyword, specializers, and reference to the link that we specialize, because one link can specialize another one. And here we say that we only want to see this part of the editor if the condition specified in this function is true. The function should show specialized. We say visible if source node should show specialized. So if you look at this function, okay, it's an extension function on the concept of abstract link, and it's very simple. It just tries to find the ancestor node of this concept and check some condition on it over here. But if we look closer, we can see that there are some extra things like this query keyword, and the return type is query boolean instead of just boolean. So there's something going on here, which brings me to the next thing, which is queries or model queries. They are somewhat parallel to behavior methods in MPS. But the main concept, the goal behind them, is to track model dependencies of executing this Kotlin function. So what parts of the model were read during execution, with the aim so that we know when something among those dependencies is changed, we know that the result of the function may no longer be valid, it's out of date, and we have to do something about it. So important to understand that it's necessary to have some kind of such mechanism, because for the editor to work, for example, because the editor has to re-highlight stuff when something changes. So how do we go about it? How do we define these query functions? So it's pretty much just plain Kotlin code with minimal decoration. So in this little snippet of code here, I've highlighted those things which make it a query function. If we remove them, it's a completely ordinary Kotlin function. So what do we see here? We see query keyword, and we see some extra parens on those parts on which we actually depend. So it's either a part of the model, like child here, or the result of another query function, like query method here. And okay, important to understand that those strangely looking double pairs of parens are not some magic syntax. It's actually a perfectly normal Kotlin expression. It's just we define on the object that query method returns, we define the invoke operator, which Kotlin allows us to do. So the second pair of parens is just calling that invoke operator. But of course it would look, yeah, and the question marks, don't look at them, they have nothing to do with this query thing, is just Kotlin syntax. And of course it would look nicer if we didn't have those extra parens, and of course one might easily forget to add those extra parens, and yeah, and they would risk kind of taking a value of something and without recording the fact that we depend on it. So that would be a bug. But the good thing is that we've done it in a way that it would be a compiler error if we forget to add those parens, so we don't forget. Okay, and since those queries are just Kotlin functions, they can be defined anywhere in your code inside the concept, then it would look really like a behavior method in MPS or anywhere else. So, okay, now I want to talk about language aspects that heavily rely on those query functionality. So it's error checking rules and scoping rules. So saying right away, no typing rules for now supported. So we're okay with that in B2B currently. So both of those aspects, the definition for them has the form of some lightweight DSL plus query Kotlin code. And again, before I jump to the examples, I want to remind that so anywhere inside the body of any of those scoping rules, we're free to use asynchronous calls the Kotlin way. So in the sense that I talked about in the beginning. And another thing is that all the model changes that would affect the results of the rule are automatically taken care of for us. So the rule will be rerun when something changes. So let's have a look at scoping rules first. So we say scopes and we enumerate scoping rules. So here, for example, we say that the node of the concept fact set provides the nodes of concept fact by this logic. And by the way, we say fact set impl here because we currently don't have code generation for concept, and we kind of maintain this tie between fact set and fact set manually here, which we will fix. Okay, and the logic for the scoping rule is pretty simple, just a collection scope of facts filtered by the condition that it's not the fact from which the request comes, so a fact cannot reference itself. We have a construct for default scope concept with an obvious semantics. Here's an example of a slightly more involved scoping rule. It's bigger, and the icons on the left over here tell us that we're actually making asynchronous calls inside the body of the rule, because we're resolving references here, and resolving references is always asynchronous in our framework. So let's look at error checking. Conceptually, it's pretty much the same. We say error checking, and we enumerate the rules. So here we say check this concept for duplicates, in this case in terms of name, of nodes in this child row. We say the same for a number of other concepts. We say check process declaration, whether it contains cycles in terms of extends relation, because processes in B2B can extend other processes in the same way like classes extend classes, and they can be cycles, and it's an error. So we check that fact here. So just to remind you, if we remove an extra pair of parens, it would not compile. Okay, the next thing is reference resolving. So one might wonder, I've already discussed scoping rules, so why this again? But in our framework is distinct from scoping rules. So using scopes to resolve reference is just a special case. And in the general case, one can define the resolvers in terms of some arbitrary Kotlin code, or instruct the framework to use the remote editor service or remote machine, what we do in biological knowledge base, to resolve references. And also, this is actually the place, reference resolving specification, is the place where we distinguish between what MPS calls dynamic and static references, because we specify some lower level details here, like what we actually want to be stored as the contents of the reference. For instance, we may want to store the name of the target node, or node ID of the target node, or something else. So yes, I think that's all I wanted to say about the framework for now. And yeah, it's all really likely to change a lot. So, and here I would like to hand it over to Simon. Thank you.
My name is Simon Alperovich, and we will look under the hood and talk a little bit more about technical details of our project. So let's start with recalling the simplified architecture of the MPS. What do we have here? We have the model persisted on disk in the XML format, and then it is loaded to the memory as an abstract syntax tree. And then it is viewed and modified by the editor, which is operated by the user. Well, the idea behind the knowledge base is absolutely the same. We have the model persisted in the database, this time in JSON format. It is loaded to the browser as an abstract syntax tree, and then it is viewed and modified by the editor, which is again operated by the user. Okay, but now, unlike NPS, we may have several users. And each user has her own version of the model in the browser. So we need to somehow synchronize their models. And as you may have heard from my colleagues, we do it with the help of an operational transformation service. The service contains the model. So each client is connected to the operational transformation service. The model is loaded from the service to the clients, and then the service processes the client changes to the model and sends updates back to the clients. And this way, all models stay synchronized on each client. Those changes are sent as comments, and an example of comment would be adding new node, deleting node, or changing the text of the property. And remember, we don't work with the text, but rather with abstract syntax trees. So we have our own operational transformation working with trees. Okay, seems fair, but we now face a small problem. And the problem is that our models could be quite big. Imagine, like on the picture, we want to complete the reference to the element from the NCBI taxonomy ontology. And in order to get the list of ontology elements, we need to have the ontology in our model. And this means we should download the ontology. But the NCBI taxonomy in the form of abstract syntax tree is several gigabytes. And we can't afford to download several gigabytes each time a user opens some document, right? So the question is, what should we do? And the answer is obvious. We add another service. This time it is called editor service. And it contains an up-to-date model, which is all nodes, including those big ontologies. And now, as you can see in the picture, the user downloads just a single root node she wants to edit, not the whole repository. And in BTB, we call it like document, as it was mentioned before. And again, this is just a single root node. And now the procedures such as give me completion menu or resolve the target of the reference are executed remotely on the editor service. Great, so let's now dive a bit deeper and take a look at the whole cycle of the editing process. We will take a look at the following scenario. The user will add a new fact to our document, and then she will invoke the completion for the reference inside that fact. So it will look like this. We will add a new fact and invoke the completion menu. Okay, let's go. So here you can see how everything is connected. We see the browser, which is connected to the operational transformation service, and editor service. And editor service is also connected to the operational transformation service. And at this point, I'd like to add one important note. The operational transformation service, for this service, there is no difference between the browser and editor service. They both communicate with the service with the same operational transformation client. So we will come to this again a bit later. Okay, going back to our scenario, the user pressing enter, then the editor in the browser reacts to the section and adds a new fact to the document. We're adding the fact. Then this change immediately goes to the operational transformation service. And then this fact is added to the model of the editor service, which, as I remind, just the same client of the operational transformation service of the browser. Okay, first part is done. Now the user will press Ctrl space and invoke the completion. Again, the editor in the browser will react to this action and ask the editor service to provide the completion menu. Now the editor service locates the editor for the fact that we just added. So we locate the editor, and now this editor will get the required list of elements from the model repository. And then the editor service returns back to the user. Okay, we're done with our scenario. Now just a couple more words about the editor service. Currently, it is used for reference resolving and completion. And as I said before, it allows us not to send the whole repository to the client. We also do the optimizations. The first one is when we resolve the reference and send the resolved target to the client, we can send only the reduced version of the node, because most of the time the client wants just the target's name, so we can cut off the target's children. And also we send only several completion items to the client, because most of the time the user doesn't want to see the thousands of elements. So this way we optimize the used memory. And we have the further plans to optimize this process, the editing process, and those things are currently when the user opens the editor for the document, we do as many resolving requests as there are references in the document. While in future, we plan just notifying the editor service about the client opening the editor, and it will send all required information with one request. The second plan is to build indexes for big scopes on the editor service. For example, the ontology I showed you, the NCBI ontology and the other ontologies, they don't change often. So we could calculate and cache the list of those ontologies, of those ontology elements, instead of calculating it each time the user asks for a completion menu. And we're planning to bring more functionality to the server. An example would be error checking. So overall, our vision is to make client as lightweight as possible and execute time and memory consuming operation on the server. Okay, great. Well, some of you may have mentioned a small detail. Let's take a look at the picture again. We have here the editor and the model in the browser. Okay, this is just a single document, but it's still part of the model. And also we have the editor and the model in the editor service. And it's not on the picture, but as I said before, we have a model when we run queries, which happens on the document service. Also, we have the operational transformation client, both in the browser and in the editor service. And it's absolutely the same. So we have the same code, and it's running both on backend and frontend, correspondingly JVM and JavaScript. And the question is, how do we do it? The answer is with the help of Kotlin multi-platform. So we run it once and write it once and run it both on backend and frontend. And this is very convenient. It allows us not only distribute the same code to the different platforms, but also easily switch to the target platform on the development time. For example, originally we had the editor completely in the browser, and then later we decided to move its part to the editor, to the editor service. So we did it without any pain because of the Kotlin multi-platform. So at this point, I would like to just add a couple of words about Kotlin. Let's go. First word is Kotlin is an amazing language. And the second, everyone should use Kotlin. Okay, a couple of words said. Okay, seriously, it's a great language and it has a lot of great features, such as null safety, data classes, extension methods, already mentioned multi-platforming, interoperability with Java, Daniil's shown you internal DSLs, and a lot more. So if you haven't already, you should definitely give it a try. Remember, Kotlin by JetBrains. Okay, let's now go back to the architecture. Here's the final overview. We have the front end where the editor is running. Then we have the back end. There's an operational transformation service, which is responsible for collaboration. Then there's an editor service, which helps the editor on the front end. And then we have the document service, where the documents are stored. And the queries are also running on the document service. And also we use the external APIs to import documents such as ontologies and React on. Okay, now just final words about our deployment process. We have the code on the GitHub. It is pulled by TeamCity, which builds the Docker image. So we use the Docker, and then we use the Amazon Web Services. This, like microservice architecture and Amazon Web Services, provide us with the easily achieved scalability. We can increase memory and add new instances without changing the code. And also, we can start and stop the services on demand. For example, we may initiate as many editor services as we want. And for example, in extreme cases, we can even initiate one editor service for one client if it would be needed. The same applies for queries. We can initiate a service when the query is started and stop it when the query is completed. Okay, that is it from my side. Thank you very much for your attention. Just one small announcement. JetBrains is currently hiring the software developers for MPS related projects, including the one we had just shown. And here's a screenshot of the vacancy. It's set here, it is for St. Petersburg and Prague, but we also have offices in Munich, Amsterdam, Moscow, and Novosibirsk. So if you would like to work with us, please do not hesitate to contact us. Great, thank you very much once again. And if you have any questions, please ask them in the chat.
All right, thank you, Simon, and everybody else for the presentation. Very interesting. I like the fact that you combined a concrete project with the underlying technology. That's always nice to see a concrete application. So there are lots of questions, and in contrast to what you might think initially, there are also questions not asked by Federico. But before we start with that, I'd just like to mention, if you want people to use Kotlin in this community, I think you know what you have to do, right? You have to implement Kotlin as a base language in MPS, get rid of the old crappy Java. And I guess once you do that, everybody here will start using Kotlin. All right, so first question by Federico. Is Web-MPS going to be open source? And when? And why not?
Okay, thank you, Federico, for the question. I will probably answer this. So the answer is we just still don't know. So it's still under development, and probably like we're definitely going to have some commercial license, but we are not sure about open source yet.
Okay, so the when is not relevant because you don't even know the if. Yeah. When will there be an opportunity to use it? Even if it's not open source, there might be some way of licensing it, right? So is there any idea when you might go live?
All right, so I'll probably talk a little bit more about our roadmap. Fortunately, it's not public, but
that was another question. Is there a public roadmap?
Okay, it's not public, but I will talk about this. So currently, our goal is to release the biology knowledge base. So we are currently releasing it internally, and we are now in the process of like finding out the people for narrow, I would say, adoption for like several people. And then lately it will after that the adoption will be like more wide, and then like the first part, like the early adoption is will take like I think a year, and in the next year like it will go public. And after we like prove that our technology is like fine, we will go public with this platform.
So this sounds like at least 2 to 3 years.
Like in 2 years, I would say, yeah.
Okay. Next question.
I would add, yeah, if you can hear, yeah, I think I would like to add, well, not about particular time, but the thing is that the priority currently is this biology knowledge base project, and it's not like Genestack folks are developing knowledge base and we are doing this framework. So we actually all work on biology knowledge base, and we spend some of our time working on the framework. So currently the priority is there. So it's feeding us the requirements and stuff like that. So yeah.
Okay, so meta comment by the moderator, we are basically out of time, but we have lots of questions left. So if you have to leave now because it's 7 p.m., then we hope to see you again tomorrow. But of course, we're going to continue with the remaining questions, and we hope that some people are going to stay around. By the way, there are also some questions about the biology, but I'll put the language questions first because that's kind of more potentially interesting for the community. So Federico asks, do you have something similar to grammar cells in Web-MPS? I think he asked that before you showed how you define the syntax with Kotlin, so that question might not be completely relevant, but I'm asking it anyway.
Well, we don't yet have something similar like grammar cells, but we will probably add it a bit later. At the moment, we will develop more like expression-like languages. So not yet, the short answer.
Okay. Federico,
okay,
are you
one
abandoning?
One thing can be mentioned. Okay, there's some kind of delay. I'm sorry.
No.
Yeah, so in the projectional editing framework, that there is not only really projectional editor in the narrow, like structured editor, but there's also this hybrid editor, which may be somewhat similar to grammar cells. I'm not completely sure about that. And in the previous incarnation of this tool, which was based on MPS generators, we generated into both projectional editors and hybrid editors. In this at this our Kotlin DSLs can result only in projectional editing, so hybrid editing is currently not used, but it's present in the framework, and so we can employ it at some moment.
Mm. Is the framework still the thing that Konstantin originally developed?
Yes. Yeah, so
Okay.
it wasn't rewritten, it was just migrated to Kotlin pretty much automatically,
okay,
with some amount of effort, of course, but yeah, it's the same.
Okay. The last question from Federico: are you abandoning projectional editing for language definition, or because it is a simpler first step to do it in Kotlin, or because you think that projectional editing is bad for developers, or for other reasons?
Yeah, this is a very good question. I actually have already looked at it in YouTube, so I had some time to prepare. Yeah, I think the correct answer would be that we're evaluating whether it would be enough for Kotlin DSLs to provide the means to specify language definition. So it's not like we want it to be projectional or want it to be textual, but it's just there are advantages in having language defined in the same code, in the same language, like the rest of your application. And it's interesting for us to evaluate if Kotlin DSLs are actually good enough for that. And I have a suspicion that for such not a very complicated task in terms of DSLness as language definition, Kotlin DSLs can be enough, but we'll see. So actually, as I said, it's all likely to change, and maybe languages will be defined in a projectional editor, either as an addition to these Kotlin DSLs, or I don't know.
Okay. Here's a question by somebody probably from Russia who wrote his name in Cyrillic letters, which I cannot pronounce. So I'm not going to give you a name. Is the mainstream MPS going to be neglected because of Web-MPS? And I swear I didn't make up the question or make up the person. It's a real question.
Okay, I really hope not, but I don't know. They've separated, so it was kind of gradual. But currently, there are two separate projects which share only ideas and expertise, so to say, but not the code.
Well, okay, I would add that we are absolutely have zero plans to neglect MPS. We are continue to support it and develop, and we just like have two separate projects, each one having its own way. But we're not planning to neglect it at all. So don't worry.
Okay. So now
yes, it just so happens that the people who are present, the people who are present right here work on that other one.
Yeah, so, and some of the people have previously worked on MPS. That might be a little bit where the question comes from, looking at you, Simon.
Okay.
So now Dimitri asks, could you share some usage experience feedback from real biology subject matter experts? how they like the tool, I guess.
Unfortunately, we don't have like real biology experts currently, but it is like our nearest plan to find one, and we will share the experience like as soon as possible.
So I hope you have some experts, but they're not currently using the tool.
Yeah, of course, we have access, yeah, and they will start using our tool very soon.
Yeah. Another question in this kind of same direction from Dimitri as well. Are there any estimates on effort required for writing contents of, for example, of a textbook with the biological knowledge base system? Or would this all be imported?
It depends, of course, of the size of the textbook. But okay, once again, we will probably answer this when we start to fill our knowledge base with the knowledge, with the help of those scientists.
Okay.
Sanjit asks, it's important.
Sorry.
I'm sorry again. Yeah. Actually, important idea is that I don't think that huge amounts of knowledge are supposed to be entered manually.
Manually, yeah.
Yeah, because this paper analyzer project is supposed to help, and which would automatically extract knowledge from papers. So, yeah, of course, manually entering a huge textbook, I think it wouldn't be a good idea.
Yeah. Yeah, that's kind of a thought that came to my mind while you were showing this. I mean, in some sense, you're building almost like a classical expert system, right? You're manually putting in the correlations and the causations and the processes. And today, in general, in many of these domains, there is kind of a trend towards somehow let machine learning do all this magically. And I'm not sure how realistic it is, but I'm surprised to see that you're trying to build something like that manually, or extracting it from some system in a way that's not probabilistic as machine learning kind of is. Sanjit asks, how is the authentication and authorization service implemented? Will JetBrains provide this, or will it have to be implemented by users?
I think we will provide it. Yeah, so it shouldn't be implemented by users.
Yeah, but it's not defined yet, I guess. That's your face tells me you haven't done it yet.
Yes.
Okay, but as far as I understand, this biological knowledge base is going to be kind of a real service, not something that can only be deployed on premises, like they say today, but kind of a real service where the user can log in and do stuff. So,
yeah. Okay, last question from Perdita. I know her name is pronounced differently, but I don't remember how. We met at a conference once. So a nerdy question, but Simon mentioned null safety as a key feature of Kotlin, which Simon loves. Whereas on day one, Marcus, said that I wouldn't bother with option types anymore in kernel F. So how does this fit together? Do you want to answer? Should I answer?
Yes, please answer. Like, I don't know what. Who should answer this question? Like,
okay, so let me give it a try. So I like null safety and option types as well, which is why I added it to kernel F. But my users, who are business people, subject matter experts, not programmers, they don't care. And so that is, I mean, the customers often prefer to work with an explicit value for nothing, and then write stuff like, if variable dot has value, then blah, else blub, right? So I guess it's different target audiences.
Okay, yeah, I agree. So we as a programmers, we love this feature.
Yeah.
Null safety.
Yes. Yes, null safety is only for real programmers. Okay, so I think this is a nice conclusion. Thanks again for the presentation.